Hey everybody, in today's lesson we're going to start looking at the chi-squared test. Now the chi-squared test is really useful for when you're trying to make inferences about categorical data. Everything we've been doing up till now has been quantitative data. So again, this is going to deal with categorical data. So specifically in this section, I'm going to show you how to come up with the appropriate hypotheses and compute what we call the expected counts so that we can do a chi-squared test for goodness of fit. And then we're going to go through how we come up with the statistic, the degrees of freedom, and the p-value so that we can actually perform the test and then come up with a conclusion. So there are going to be three tests that we're going to look at. Now they each use the chi-squared statistic. However, the tests are all subtly different. In today's lesson, we're going to be looking at the chi-squared goodness of fit, which is basically we're comparing distributions and we're seeing if one distribution is going to be a good fit for the distribution that that it's supposed to be like. In the other ones, we're going to be testing for homogeneity, which is where we try to see if two or more distributions are linked with one another. And then for the chi-squared test for independence, that's going to allow us to determine if there's convincing evidence of an association between the variables in the population at large. But for today, we're going to be just looking at the chi-squared goodness of fit test. So I'm sure you've all had M&Ms. Okay, so the company says, excuse me, that on average, the candies will contain 13% of browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. So what we want to be able to do, is we want to be able to get our bags of M&Ms and see if this is really true. Okay, because I don't know about you, I'm not a big fan of the brown ones, so I would hate it, if they're saying that there are 13% of browns and reds, and in fact they were say like 50%. I wouldn't be a happy consumer. So this one-way table that you see right here summarizes the data from a sample bag of M&Ms. And in general, one-way tables display the distribution of categorical variables for the individuals in the sample. So you can see right here that in our bag of M&Ms, we had 60 M&Ms, 9 of those were blue, 8 of those were orange, 12 were green, and so on. So that means the sample proportion of blue M&Ms is about 9/60. So about 15% was blue. Now, we were told that it should have been about 24%. So we could look at that and, come up with our regular, test for proportions. And there we have two hypotheses right there. But the problem is we've got so many other colors going on that we want to be able to test them all. We know there might be a slight deviation in one or two of the colors, and we know that's going to affect the rest. But we want to see if the distribution in our sample is significantly different, or maybe it's the same or not significantly different enough from the original assumed distribution that the M&M's company is putting out there. Now, we don't want to do that Z test. So instead, what we do is a chi-squared statistic. So like I said, performing one sample Z tests for each color, it wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much from the one claimed by the company as this bag does. So for that, we need a new kind of test. And that is what we call the chi-squared goodness of fit test. So the way it works is, first of all, when you're doing your hypotheses, you tend to write them as a sentence. So in this case, the null hypothesis would look like this. The company's stated color distribution for M&M's milk chocolate candies is correct. So that kind of takes everything into account. Basically, what they stated for all the different color proportions is correct. So that means the alternative one is that, hey, it's not correct. The company's stated color distribution for the M&Ms is not correct. So that's pretty much what it's going to be like most of the time. Now, you can also write it as symbols like that, okay, where you have the proportion of blue is 0.24, the proportion of orange is 0.20, etc., etc. And then the alternative one is basically saying, hey, at least one of those proportions is going to be incorrect. Because if at least one of those is incorrect, that affects everything else, which means it affects the total distribution. Personally, I would always choose to write it as a sentence like you saw in the previous example. So the idea of a chi-square goodness of fit test is this. We compare the observed counts from our sample with the counts that we would expect to get, all right? Because if the distribution was really the same, what we would observe to get should be the same as what we expect to get. If they're different, then that means that the company's distribution claim is probably not going to be correct. So, assuming that the color distribution stated by Mars is true, 24% of all M&Ms are blue. Okay, so for a random sample of 60 candies, the average number of blue M&Ms should be 24% of 60, which is about 14. So that's what we call our expected count. And then we can do the same thing for all the other categories. So we would expect 20% of those 60 M&Ms to be orange. So we would expect 12 to be orange. We would expect 9.6 to be green. It's okay if you have a decimal there. I know you can't get 0.6 of a green M&M. We would expect 8.4 to be yellow, and so on. So then this is the important part. We want to come up with a table that compares our observed values with our expected values. So as you can see, there are some differences. Some of them are big, some of them are not so big, especially the one for the brown. So our goal here is to take everything into account and see if, in general, our expected distribution is different from our observed distribution. So, to see if the data can give convincing evidence against the null hypothesis, we compare all the observed amounts with the expected amounts. And you could look at a diagram like this, a graph like this, and you can see that there are some similarities and there are also some differences. So, like I said, we see some fairly large differences between the observed and expected counts in several color categories. So then the question is, how likely is it that the differences, these differences, large or small, would occur just by chance? So to answer this question, we're going to come up with what we call a chi-squared statistic. So the chi-squared statistic, again, it's used for tests for goodness of fit, it's used for tests of homogeneity, and it's also used for tests of independence, which we'll look at later on. Again, today we're just looking at our goodness of fit. But it's the same test statistic for every single test. And it's always this. It's the sum of the observed values minus the expected values, and you square those, all divided by the expected. And the reason that we're squaring it is because we want to look at our distances, and we don't want those distances to be negative. It's kind of like a standard deviation thing. All right, so let's have a look here. So we've got our observed, we've got our expected, okay? And as you can see, we're figuring out a different value for each one. So for the blue, we observed 9, we expected 14.4, so we subtract them, square it, and then divide by what we would have expected it to be, okay? And then we do that for all of the different colors. And then the sigma notation means that we add up all those values. So we have a chi-squared test statistic of 10.18. Now, I'm just going to very briefly show you how to do this on the calculator. Okay, so bear with me. So here's our calculator. So the first thing you want to do is you want to go into Stat, and then you want to go to your tables. And we're going to put in all these values. So just bear with me. I'm going to go back from screen to screen. So we have 9, 8, 12, 15, 10, 6, 9, 8, 12, 15, 10, 6. So there's all my values right there. And then for the expected, we have 14.4. Oops. 14.4. All right. We also have 12. Should make that 14.4. We have 12. We also have 9.6. We have 8.4. You could fast forward this part if you want. We've got 7.8. And then we've also got another 7.8. Okay, so apparently I missed one there because, oh, that's right, I shouldn't have 14.4 at the end there, so we'll delete that. So there we go. So we've got all my observed values in the left column and all my expected values in the right column. There we go. Observed, expected. So on the calculator, this is how you can come up with a chi-squared test statistic. Go up and highlight L3, open up parentheses, and then do second L1 minus second L2. Close parentheses, square, and then divide by, again, the expected values, which were the L2 column, so second L2. So that gives you all of the different contributions, okay? So what we're going to do next is we're going to add up all of those values. So the easiest way to do that, we'll get out of that, is to go to second list, go across to math, and you'll see that number 5 gives you the sum. So we're going to do the sum of sum of L3, because that's where all those values are, and then we'll press enter. So there you go, we get a chi-squared test statistic of 10.179, so about 10.18, which agrees with what we have on the screen now. Okay, so now we've got the test statistic. What do we do with it? Well, think of the chi-squared as a measure of the distance of the observed counts from the expected counts. So large values of chi-squared are stronger evidence against the null because they say that the observed counts are far away from what we would expect the null to be if it were true. Small values of chi-squared suggest that the data are consistent. So let's have a look at the chi-squared distribution. So the chi-squared distribution, it's not a normal distribution, okay? And it's a right skewed distribution all the time. And it allows only positive values because the chi-squared test statistic can never be negative. So in order to do this test successfully, we always need the expected counts to be at least 5. And we'll get into the conditions in a second. Now, the chi-squared statistic is close to a chi-squared distribution with degrees of freedom equal to the number of categories minus 1. So as you can see there, as the number of categories increases, it starts to get slightly more less skewed. And again, big distinction here, when we use the degrees of freedom, it's the number of categories minus 1, not the sample size. So make sure you remember that. Okay, so we computed the chi-squared statistic for our sample to be about 10.18. And because all of the expected counts are at least 5, that's going to follow a chi-squared distribution reasonably well. So in order to find the p-value, there are 2 ways of doing it. I'm going to show you how to use the table and how to use the calculator. So to use the table, okay, we go to the very, very last tables in our formula sheets. It's called Table C. And we look in the degrees of freedom row 5. Because remember, there were 6 categories. 6 minus 1 is going to give you 5. So it gives you some values like that. Now we want to see where our test statistic lies. So if you look right there, our value of 10.18 is going to lie between 9.24 and 11.07. That means our p-value is going to be somewhere between 5% and 10%. So conclusion-wise, since our p-value is between 5% and 10%, it's greater than the 5% significance level that we were going to be using. Therefore, we're going to fail to reject the null. We just don't have sufficient evidence to conclude that the distribution of M&Ms is incorrect. Now, here's how you can do it using the calculator. So remember that value, 10.18. So let's go back here. So what we do is, because it's a distribution, it's the chi-squared distribution, we want to go here to where it says distribution. So second, distribution, and then we're going to scroll down to number 7, which is the chi-squared CDF. And we're going to put in 3 values. So the first value is our test statistic, which was 10.18. comma, and then just like in the normal distribution, I'm going to use a really, really large value. And then the last value I have to type in is my degrees of freedom, which remember in this case was 5. Close parentheses, and you can see you get a p-value of 0.07. Again, stating that it's between 5% and 10%, but this time we can find it out much more accurately. All right, I'm going to pause for right now. I'm going to give you another video with another example. But again, if you have any questions, please reach out to me and let me know. Okay, thanks very much, everybody.